Hi everyone, I hope you had a great weekend. Hope you were able to find some time to celebrate your prom. So I want to start the next unit. We have three very important sections in this unit. It kind of puts everything we know together and gives us a couple more ways to apply derivatives. So we'll actually look at some real-world situations in this chapter. The first section is curve sketching. So after this section, we will be able to make a very detailed sketch of a curve using all the algebra, pre-calculus, and calculus skills we have. So I'm not going to go through the whole note. I'm just going to skim through the first little bit and then do one graphing example. So curve sketching we've done in the past. We did it in level 1 with lines. We did it in level 2 with quadratics, and then we completed it in pre-calculus with rationals and radicals, and now we're doing it in calculus with all of that. So on top of what we already can do, now we need to be able to figure out where the max and mins occurs, and that's where we use the derivative, and where the function is increasing and decreasing, which we've already talked about. So essentially we need the original function f of x, we need the derivative f prime of x, and we need the second derivative f double prime of x. So we use f of x to figure out where all the points are. We use f primed of x to figure out where the graph is increasing or decreasing and where the max and mins are. And we use the second derivative, f double prime of x, to figure out basically which way my graph arcs or is curving. And we'll get to that one in a minute. So for the first derivative, essentially if it's positive, your line is increasing up to the right. So see how this one's arced this way and the other one is arced this way. So that's curvature. One is called concave up and the other is concave down. And that comes from the second derivative. So increase or decrease, greater than or less than. If the derivative is greater than 0, it's increasing. If the derivative is less than 0, it's decreasing. If the derivative is equal to 0, that means we're at a max or min or a flattening. So it might actually flatten out and continue on in the same direction. If the derivative is undefined, that's where we get into our special kind of properties. So it could be a vertical asymptote, a POD, a corner, a cusp, or a vertical tangent. And we looked at all those in a previous section. So that's the first derivative. The notes as you move forward explain what's going on and give you some examples. I'm not going to go through all that. When the derivative is 0, we get what we call a critical value. Okay, so if the derivative is 0 at 3, then 3 is a critical value. So this page here explains that. Then we look at concavity. And concavity is your curvature. So if you can sit in the curve, it's concave up. If the curve is above your head, it's concave down, right? So the dome type shape is concave down, and the valley type shape is concave up. And again, this is based on the second derivative and if it's positive or negative. So positive is concave up, negative is concave down. And if you notice, this would be a min and this would be a max. So concavity usually changes in between a min and a max, or vice versa. So you can see, right, curved up, curved down, curved up, curved down. So if a function is increasing and the line is getting steeper, it's concave up. If a function is increasing and the line is becoming less steep or flattening out, it's concave down. And then the opposite is also true. So there's lots of little mental math things you can use with the calculations to figure out concavity. And again, same properties apply, right? So you've got concave up to concave down. You've got a flattening. This is what a flattening looks like. And then you've got a vertical tangent, which means the derivative or the second derivative would be undefined. So where concavity changes, it's called inflection points. So where concavity is 0. Sorry, not changes. It could change. It could not change. Right? Down, oh, up, and then up and down. So where concavity changes, sorry, it is an inflection point. All right, and there's a little note there. It says not every hypercritical value is an inflection point. So critical values are when the derivative is 0. Hypercritical values are when the second derivative is 0. And a little note here, you can see that in the middle of this min and this max, you've got a change in concavity. And in the middle of this max and this min and max, you've got a change in concavity. So that's really an easy way to get the point. If you know that you got a max at 0 and a max at 1, then in the middle it's going to be an inflection point. So a few new terms there. This is just a summary of one way to graph it. It doesn't really matter the order. I just do asymptotes first with limits if I need to, then all of my intercepts. Then I do the first derivative stuff and the second derivative stuff. So I'm going to put these notes up filled in when I get this video done. I'm going to skip the first two. I want to do the last one. And if it's anything other than a polynomial for a sketch, you'll get the first and second derivative. So the first one example was a polynomial, so you can do the derivative fairly quickly, mental math. But anything else that's complicated for graphing, you'll get the first and the second derivative. So you just got to do the calculus or the algebra in this case. So if we follow our steps, this is a radical to 2 cubics. So I'm just going to label them. So 1 would have been the asymptote stuff. So here, 2 cubic root x5 minus 5 cubic root x4, there's no asymptotes. For this graph. Right, there's no undefined values because they're cubics. So you can have negatives. If they were square roots, then it'd be a little bit different. But cubic roots, you're allowed to have negative values. So there's no restrictions. Fix this. Asymptotes. Okay, so we don't have to do any calculation there. If you look at the previous example, there are asymptotes. 2 is your intercept, so this is basically for your y-intercept. You let x equal 0. So we're trying to find f of 0. So if we put 0 into our original function, we get 0. So there's a y-intercept at 0. You can put the points in as you go, or you can wait till the end. So 0, 0. I usually wait till the end because I don't know what my scale is going to be until I see all the points. But 0, 0 is an easy one. So that point is on my graph. Now I need my x-intercepts. So that means I have to solve the function for 0. So 0 equals 2. And I'm going to change it to exponential because it's a little bit easier to deal with. So cubic root of x5 is 5/3. And then minus 5x to the 4/3. So solving for 0 means we got to factor if we can. So there is a common factor here of 4/3. So I can factor out x to the 4/3. And I'm left with 2 x to the 1/3 minus 5. So this is just the fact that these are rational doesn't change the rules. This is still just x to the 4/3 equals 0, which means x equals 0. So that's the point I already got. It's an x-intercept and a y-intercept. This one here, 2x to the 1/3 minus 5 equals 0. Take over your 5, divide by 2. X to the 1/3 equals 5 over 2. So the opposite of 1/3 would be the power of 3. Right? So we want to do the reciprocal power rule. A little bit of algebra going on here. So the x would equal 125 over 8. So this point is 0, 0, and this point is 125 over 8. You can change that into a decimal. and 0. So 125 over 8 will give me 15.6. So an approximation, but it does tell me that my scale has to be fairly big here. So that's another point that I've got to add in there. So I'm pretty confident now I can make a scale based on that. If I go up by 2s, 2, 4, 6, 8, 10, 12, 4, that's not big enough. If I go up by 3s, 3, 6, 9, 12, 15. So 3s would work. So 15.6, 3, 6, 9, 12, 15. So about there. Again, we don't have to be exact. Even though it's a more accurate sketch than we're used to, it's still a rough sketch. Now we're on to the calculus part of the calculations. So calculus, the derivative gives us the max and min or increase decrease. So we're given the function here. We want to know when this function is equal to 0. So if we've got a fraction equal to 0, we don't need to worry about the denominator. So we're just worried about when the numerator equals 0. So it's already factored for us. So f prime equals 0 when, I keep going back up, 10 cubic root of x cubic root of x minus 2 equals 0. Again, like before, we've got two answers. So this is when is 10 cubic root of x equal to 0? That happens when x is 0. When is this equal to 0? When the cubic root of x equals 2. Well, again, what cubic root of x will give me 2? If I cube, I don't want that to be red. If I cube both sides, I know that x has to be 8. So at 8, the derivative of 0. So that's a max or min. At 0, the derivative of 0. So that's a max, min, or flattening for both of those. Not just 0, but at 8 as well. So I need to now define the point on the graph. So I have to put 8 into the original equation. Not this one. This doesn't help me. So the point for f of 8 in the original equation, so you can see it gets tangly, especially the more complicated the equation is. So I've got to put 8 in here. So 2 times cubic root of 8 to the power of 5 minus 5 times cubic root of 8 to the power of 4. So 2 cubic root of 8 to the power of 5 minus 5 cubic root of 8 to the power of 4. So that works out to 2. Cubic root of 8 is 2. 2 to the 5 is 32. Minus 5. Cubic root of 8 is 2. 2 to the 4 is 16. So we're getting 2 times 32 minus 5 times 16. And I'm not too worried about all these workings. If you just said f of 8 equals, that will be fine. And it works out to negative 16. So the point, there's a point on the graph at 8 and negative 16. And it's a max or min, most likely, but it could be a vertical tangent. So now where was 8? 3, 6, 9. So 8's in here. Negative 16. 3, 6. So if we use 3's in all directions, so 3, 6, 9, 12, 15, negative 3, negative 6, negative 9, negative 12, negative 15, negative 18. So 8 would be about here, and negative 16 would be about there. So not a great place to put it, but again, it's where it has to go. Then what we do with f of x, we do a sign diagram, or f prime of x, And the sign diagram would include any values that are 0 or undefined. So here we got a value 0, a value at 8. There's no undefined parts. So undefined in the original would also be undefined here. So in order to use a sign diagram, we use the actual f of x function. So if I put in a negative number less than 0 in here, I will get a positive value, which means the slope is increasing. If I put in a number between 0 and 1, or 0 and 8 in here, I'll get a negative value. And then if I put in a number bigger than 8, I will get a positive value. Okay, so that means the graph is increasing, decreasing, increasing. So it looks like this is a max, and this is a min. And that's step 5 to indicate if it's max or min. Then the last 3 steps is doing this again, but for the second derivative. So we're almost done. It's a long process to do a graph. I'm only going to give you 1 on your skill check. Most likely it won't be a radical, it'll be a rational or a polynomial. So 6 is the second derivative, and again it's on top, it's up here, it's listed, you don't have to calculate it. And for letting that equal 0, we don't need to worry about the denominator, but the denominator is important because it tells me the graph is undefined at 0. Okay, so, or not the graph, sorry, the second derivative. So f double prime at 0 is undefined. So that means there's something going on there. In this case, it means there's a cusp. And if you choose, or corner, sorry. If you choose a corner or a cusp, it really doesn't matter which one when you're sketching it. You can take a look at the actual graph on Desmos to figure out what it actually is. But a corner and a cusp are going to look very similar in most cases. So now we work out the other part of this. So we want to know when f double prime is equal to 0. Again, we don't need to worry about the numerator. We're just worried about when the denominator. We're just worried about when the numerator is 0. So the numerator is 0 when 20 outside a cubic root of x minus 1 is 0. So this part is the only part we're worried about. So when is the cubic root of x minus 1 equal to 0? When the cubic root of x is 1, which means when x is equal to 1. So now we need to calculate what f of 1 is. F of 1, if you look at your equation and you plug it in, you're going to get negative 3. And that's fine. That's all I need to see. I don't need to see the full calculation, even though I did it over here for f of 8. So we've got a point at 1 and negative 3 we can put on the graph, and that's where concavity changes. So that's 6. 7 would be the sign diagram for double derivative, second derivative. And the only point where the second derivative is 0 is at 1, but we've also got it undefined at 0. So we've got to use both of those. So 0 and 1. Now what happens if you put a number less than 0 into the second derivative? You would get negative. If you would put a number in between 0 and 1 in the second derivative, you will also get negative. And then if you put a number in between or greater than 1 into the second derivative, you get positive. So 8, the next step would be to determine what's going on with these. So here at 1, this is an inflection point. And then negative, negative, where it's undefined, this is going to be a corner or cusp. Okay, so let's finish our graph. Again, with the graph is rough, so I know there's 1 and negative 3. Okay, so I know that my graph is increasing, so slope is up, but it's concave down. You don't have to exaggerate it. You can if you want. So I'm just going to start down here. I don't need to calculate any of these points. Go up there. Now, it's not turning. It's going sharply to that point. And then this is also concave down. So it's like a V there, a corner. And then now it switches to concave up. And again, you can't really see it here, but concave down, concave up, rough stretch. This is a min, so we'll do a little U. Tighten it up a little bit. So we'll go down here, we'll bounce, and then we go on up through that last point. All right, so this is kind of the tricky part. The rest kind of falls into place. And that's kind of the reason I wanted to do this one, because it's a little bit more challenging. So very long video today. I apologize for that. There's no way to get through this any faster. So that's the graph. You can see with calculus we were able to add a little bit more detail. Your skill check on Wednesday will be a polynomial or a rational. It won't have a corner or a cusp, but it could have asymptotes. That's it for now, and I'll post the skill check on Wednesday.